What if I told you that the key to bending time itself might be lurking in the darkest corners of the universe? Picture a place so powerful, it twists space like taffy and slows time to a crawl where a single second for you could mean years passing for someone else. This isn't science fiction. It's the mind-bending reality of black holes, cosmic monsters with gravity so intense they warp the very fabric of existence. And here's the wildest part. These celestial anomalies might just hold the secret to time travel. Think about the grandfather paradox, the classic time traveler's nightmare where going back to change one event could erase your own existence. Now imagine a black hole's event horizon, the point of no return where time and space swap roles. Could crossing that boundary rewrite history or create alternate timelines? Scientists have spent decades untangling these questions, and the answers are stranger than anything Hollywood could dream up. From wormholes acting as cosmic shortcuts to singularities where physics itself breaks down, the line between reality and theory blurs in ways that'll make your head spin. In this video, we're diving into 30 of the most astonishing theories linking black holes and time travel, each one a puzzle piece in humanity's quest to unlock the universe's greatest secrets. You'll discover how a dying star's collapse might birth a time machine, why some physicists believe every black hole contains a universe of its own, and whether we could one day harness these phenomena to journey across epochs. Strap in, we're about to explore the edges of known science where the impossible starts to feel within reach. The universe is far stranger than we've been taught, and the truth, it's waiting just beyond the event horizon. Einstein and his colleague Nathan Rosen once proposed something so radical it could rewrite the rules of space and time, hidden tunnels threading through the cosmos like cosmic subway lines. These theoretical passages, now famous as wormholes, aren't just sci-fi fodder. They're legitimate solutions to Einstein's equations, bending spacetime so drastically that two distant points could touch, turning a 1,000-year journey into a single step. Picture folding a piece of paper until two dots nearly kiss. That's the power of an Einstein-Rosen bridge. But here's the catch: traversable wormholes, the kind you could actually walk through without being shredded by gravitational forces, would need something bizarre to stay open: exotic matter. Not just any material, but matter with negative energy pushing against gravity to keep the tunnel from collapsing. The problem: we've never found proof such matter exists in nature. Even if we could create it, the slightest disturbance, a single photon out of place, might trigger a catastrophic collapse, snapping the bridge shut like a cosmic bear trap. Movies like Interstellar make wormhole travel look graceful, a serene glide past swirling starlight. Reality would be far messier. The forces near a wormhole's throat could stretch you into spaghetti before you even reach the other side. And then there's the time problem. Cross one of these bridges and you might not just move through space. You could leap forward or backward in time, depending on how the wormhole twists. Some theories suggest these tunnels could even connect parallel universes, turning time travel into a multiverse odyssey. So are wormholes just a beautiful mathematical daydream, or could they one day become humanity's greatest shortcut? For now, they live at the edge of possibility where physics meets imagination, and the universe keeps its most tantalizing secrets just out of reach. Now let's talk about one of the most bizarre possibilities in physics: closed timelike curves, or CTCs. These are theoretical paths through spacetime that loop back on themselves like a cosmic Möbius strip, allowing an object, or even a person, to travel back to their own past. And black holes might just be the universe's natural time loop factories. According to Einstein's general relativity, the extreme gravity near a black hole doesn't just bend space, it twists time into knots. Near the singularity, where gravity becomes infinite, the equations suggest spacetime could curve so radically that a path might circle back to an earlier moment. Picture drawing a line on a piece of paper, only to have it wrap around and reconnect with its own starting point. That's a closed time-like curve, a literal shortcut to yesterday. But here's where things get dicey. Stephen Hawking famously proposed the chronology protection conjecture, arguing that nature might have a built-in safeguard against such paradoxes. Quantum effects near a CTC, like a flood of particles gaining infinite energy, could destabilize the loop, collapsing it before any time traveler could exploit it. Think of it as the universe's firewall against rewriting history. Visualizing this is tricky, but spacetime diagrams help. Imagine a graph where time runs vertically and space horizontally. Normally, world lines, the paths objects take, move steadily upward, but near a black hole, those lines can spiral inward, crossing over themselves like a tangled ball of yarn. If one of those loops closes, congratulations, you've just found a CTC. The implications are staggering. Could a future astronaut orbit a black hole and emerge in their own past? Would they meet a younger version of themselves, triggering a paradox? Or does Hawking's conjecture mean these loops are purely mathematical mirages, forever out of reach? For now, the debate rages on one of the many mysteries lurking in the shadow of a black hole's infinite gravity. Einstein's theory of relativity revealed something astonishing about black holes. They don't just warp space, they warp time. The closer you get to one of these gravitational monsters, the slower time ticks for you compared to someone far away. This phenomenon, called time dilation, turns black holes into nature's own time machines. Imagine orbiting just outside the event horizon, where gravity is so intense that a single hour for you could mean decades, or even centuries passing back on Earth. The movie Interstellar brought this idea to life with Miller's planet, a world so close to a black hole that 1 hour there equals 7 years elsewhere. While the film took creative liberties, the science behind it is real. Einstein's equations show that time isn't a fixed universal clock. It's flexible, stretching and compressing under gravity's influence. Near a black hole, this effect becomes extreme. A clock ticking at the edge of the event horizon would appear to slow to a crawl for distant observers, as if time itself were struggling against an invisible weight. But here's the catch. Harnessing this as a time machine comes with deadly complications. The same gravity that bends time also creates tidal forces strong enough to spaghettify anything that ventures too close. Picture the difference in gravity between your head and your feet becoming so extreme that your body stretches like taffy. Long before you could benefit from time dilation, you'd be torn apart atom by atom. Even with futuristic technology, surviving such an environment would require materials that defy physics as we know them. And then there's the paradox of return. Suppose you could orbit safely near a black hole, experiencing just a year while centuries pass on Earth. By the time you returned, everyone you knew would be gone. You wouldn't just travel through time, you'd be exiled from your own era. This isn't just theoretical. Astronomers have observed time dilation in action near supermassive black holes, where light from stars gets redshifted, stretched into longer wavelengths as it struggles to escape gravity's grip. So while black holes offer a tantalizing glimpse of time travel's potential, they're also a reminder of nature's ruthless fine print. The universe may allow us to manipulate time, but never without a price. For now, these cosmic time warps remain both a scientific marvel and a chilling warning. Some doors, once opened, can't be closed. What if the key to time travel wasn't just a black hole's gravity, but its spin? Enter Kerr black holes, cosmic whirlpools so violent, they don't just warp space-time, they yank it into a frenzied dance. Named after physicist Roy Kerr, who cracked their math in 1963, these rotating monsters aren't like their static cousins. Instead of a crushing point singularity, they harbor something far stranger, a ring singularity, a gravitational maelstrom where the known laws of physics twist into knots. Picture a spinning drain dragging nearby water into a spiral. Now imagine that drain is a black hole and the water is space-time itself. This is frame dragging, an effect so extreme near a Kerr black hole that space and time get whipped into a vortex. The faster the spin, the more spacetime stretches like taffy, wrapping around the black hole like a cosmic whirlwind. And here's where it gets wild. If you could skim close enough to this spinning abyss without falling in, the dragged spacetime might just twist into a loop. A path that circles back to an earlier moment in time. Unlike Schwarzschild black holes' static, spherical traps with a single crushing singularity, Kerr black holes offer a glimmer of hope for survival. That ring singularity, it's theorized to be a gateway rather than a dead end. In theory, an object could pass through the ring's center, emerging into a mirrored universe or even another point in time. But the risks are apocalyptic. The forces near the ring would shred matter into quantum confetti, and the radiation from the black hole's accretion disk would fry anything approaching. Even if you survived, navigating the spacetime loops would be like trying to walk straight in a hurricane. Kerr's equations suggest something even more radical. These spinning black holes could host closed time-like curves naturally. No exotic matter, no wormholes, just the raw, twisting power of a black hole's rotation bending time into a pretzel. But don't pack your time travel suitcase yet. Hawking's chronology protection conjecture still looms, and many physicists argue quantum effects would destabilize any time loop before it could be used. Yet, Kerr black holes remain a tantalizing what if, a reminder that the universe's rulebook might still have pages we haven't turned. For now, they're the ultimate cosmic roulette wheel. Spin the right way and you might just beat time itself. Black holes might dominate our cosmic nightmares, but their theoretical opposites, white holes, could rewrite the rules of time itself. Picture a black hole running in reverse. Instead of swallowing everything that crosses its path, a white hole violently expels matter and energy, spewing it out like a cosmic fountain. These hypothetical objects emerge straight from Einstein's equations, mathematically valid yet never observed. If black holes are the universe's drains, white holes would be its fire hoses, flinging particles outward with such force that nothing could ever enter them. The connection to time travel. Some theories suggest white holes aren't just space oddities, they could be the other end of a black hole's tunnel, a doorway to another time or even another universe. Imagine falling into a black hole's crushing depths, only to be vomited out through a white hole in a distant galaxy or a different era entirely. Russian cosmologist Igor Novikov even proposed that a black hole and white hole could be linked by what he called a wormhole without a throat, creating a seamless bridge through spacetime. But why haven't we found one? White holes defy the second law of thermodynamics, which says entropy disorder always increases. A white hole's explosive nature would essentially undo entropy, making them statistically improbable. Some physicists argue they might only exist for fractions of a second before collapsing into black holes, like a cosmic hiccup. Others tie them to the Big Bounce theory, where our universe's Big Bang was actually a white hole eruption from a previous universe's collapse. The implications spiral outward from there. If white holes exist, could they be portals to alternate timelines, or are they mathematical ghosts, tantalizing possibilities that the universe simply forbids? For now, they linger at the edge of physics, a reminder that time's arrow might not be as straight as we think. Stephen Hawking's revolutionary insight about black holes wasn't that they're eternal, it's that they evaporate. Tiny particles, now called Hawking radiation, slowly leak out from the edge of a black hole's event horizon, causing it to lose mass over unimaginable timescales. But what if this quantum whisper isn't just a death knell for black holes? What if it's also a hint about time's secret backdoor? At the quantum level, empty space isn't empty at all. It's a seething foam of particles and antiparticles popping in and out of existence. Near a black hole's event horizon, these quantum fluctuations get twisted by extreme gravity. One particle falls in while its partner escapes, carrying away energy. This is Hawking radiation, and it suggests something wild: information. The blueprint of what fell into the black hole might not vanish forever. Instead, it could get scrambled into the radiation, a cosmic game of teleportation where data jumps across time and space. Recent breakthroughs in solving the black hole information paradox have added fuel to this fire. Some physicists argue that Hawking radiation isn't random noise, it's a scrambled code, preserving the history of everything the black hole consumed. If we could decode it, might we reconstruct events from the past? Even more radical, could quantum entanglement, the spooky connection between particles, allow microscopic time leaps? Imagine a particle near the event horizon becoming entangled with its past self, creating a bridge across moments. The math gets dizzying here. Quantum teleportation already allows particles to share states instantaneously across distances. Near a black hole where time stretches and warps, could entanglement stretch temporally instead of just spatially? Some models suggest yes, that Hawking radiation's quantum links might form fleeting pathways through time, like stepping stones across a river of causality. Of course, this isn't a ticket for human time travel. These quantum jumps would operate on scales smaller than atoms, lasting fractions of a second, but the implications are staggering. If time can bend on the quantum level around black holes, it hints that the universe's rules might be far more flexible than we thought. Hawking's radiation might not just solve the information paradox, it could rewrite our understanding of time itself. Forget black holes. What if you could build a time machine from scratch using nothing but a really impressive drill bit? Enter Frank Tipler's outrageous idea, the Tipler cylinder. Picture a cosmic-sized pole, denser than a neutron star and stretching infinitely through space, spinning so fast it nearly cracks the speed of light. This isn't some cartoon gadget. It's a serious proposal from a physicist who dared to ask if we could twist time into a pretzel using pure engineering. At the heart of Tipler's theory lies a mind-bending quirk of general relativity. Massive rotating objects don't just bend space, they drag it along like taffy. The faster the spin, the more space-time warps around it. A cylinder spinning at relativistic speeds would create a whirlpool of time, looping back on itself so tightly that following a precise spiral path around it could send you hurtling into your own past. No event horizons, no singularities, just pure, dizzying motion bending causality until it snaps. But here's the cosmic fine print. Tipler's design requires materials so extreme they might as well be magic. The cylinder would need infinite length to avoid collapsing into a black hole under its own absurd density. Even a single kilometer-long segment would weigh more than our sun, and spinning it fast enough to warp time would demand energy exceeding the entire output of a galaxy. Oh, and it'd also need to be perfectly rigid, no bending or wobbling allowed despite forces that would shred any known substance. The universe seems to mock our ambitions here. While Tipler proved the math checks out, nature appears to have vetoed the ingredients. Negative energy, infinite strength, flawless construction. It's like a recipe that demands unicorn tears and dragon scales. Yet the cylinder remains a tantalizing thought experiment, proving that black holes aren't the only way to wrangle time. They might be the universe's ready-made time machines, but Tipler dared to ask, what if we built our own? For now, his spinning monolith sits firmly in the realm of not impossible, just ridiculously improbable. But in a cosmos where pulsars spin hundreds of times per second and neutron stars crush atoms into poster, who's to say what engineering feats might one day lurk in humanity's future? The Tipler cylinder isn't just a time machine, it's a challenge flung at the feet of physics itself. Black holes don't just bend space-time, they might also flip time's arrow on its head, and the key lies in a concept as mundane as it is profound: entropy. You've heard entropy described as the universe's march toward disorder, the reason coffee cools and eggs don't unscramble themselves. But inside a black hole, entropy behaves in ways that defy intuition, thanks to physicist Jacob Bekenstein's groundbreaking work. He shocked the scientific world by proving black holes aren't cosmic vacuums, they have entropy, and a lot of it. In fact, a black hole's entropy is proportional to its event horizon's surface area, meaning the larger the black hole, the more chaotic its hidden depths. Here's where it gets eerie. For an observer outside the black hole, entropy always increases time's arrow points forward as usual, but for matter falling in, the rules might reverse. Imagine a book tossed into a black hole. From our perspective, it gets shredded by tidal forces, its information smeared across the horizon like ink dissolving in water, entropy rising. Yet from the book's perspective, as it crosses the event horizon, the radiation it encounters could appear as a perfectly ordered signal, like rewinding a scrambled TV channel into a clear broadcast. Some models suggest that inside the black hole, entropy decreases, effectively reversing time's arrow for the infalling object. This paradox ties into one of physics' deepest mysteries, why time flows forward at all. The macroscopic universe obeys the second law of thermodynamics, where entropy always climbs. But black holes hint that gravity trumps thermodynamics in extreme regimes, creating pockets where time's arrow might spin backward. Einstein's math even suggests that a black hole's interior could be a mirrored universe where entropy runs in reverse, a cosmic, anti-time zone. Yet this isn't a free pass for time travel. While microscopic particles might experience this reversal, anything larger would be torn apart long before noticing, and the reversal only applies inside the black hole, no rewatching history from the safety of Earth. The event horizon acts as a one-way gate between these two temporal realms, a barrier as strict as it is mysterious. So while black holes tease us with glimpses of inverted time, they also enforce a brutal rule: to flirt with reversed entropy, you must surrender to gravity's ultimate grip. It's a reminder that the universe guards its paradoxes fiercely, offering breadcrumbs of possibility, but only to those willing to step beyond the edge of reality. What if time isn't a fundamental part of the universe, just a side effect, an illusion painted onto the cosmic canvas? This is the startling premise of the holographic principle, a theory that suggests reality as we know it, including time, might be nothing more than a projection. Picture a black hole's event horizon like the surface of a DVD. All the information about what's inside every star, every atom, every moment could be encoded there in microscopic pixels, just as a movie's entire story fits onto a disk's two-dimensional surface. Leonard Susskind, one of the theory's pioneers, argued that black holes don't destroy information when they swallow matter. Instead, they imprint it onto their boundaries like cosmic graffiti. If that's true, then time, the flow we experience as unshakable, might just be a hologram emerging from how that data interacts. Think of it like a video game. The world feels real as you move through it, but underneath, it's all just code being rendered frame by frame. In this view, time travel wouldn't require bending spacetime, just rewriting the data like editing a save file. The implications are dizzying. If time is an illusion born from quantum information, could we hack it? Simulations like the Matrix toy with this idea, suggesting our reality might be a construct, but the holographic principle takes it further. Even in a purely physical universe, time's arrow could be a shadow of deeper, timeless laws. Imagine standing outside a black hole, watching its surface flicker with encoded history. If you could decode it, you might play back events from the past, not by moving through time, but by reconstructing it like reassembling a shattered mirror. Critics argue this reduces time to a mirage, stripping it of its intuitive flow. Yet experiments with quantum entanglement hint at something stranger. Particles can remember their past states in ways that defy linear time. Could black holes be the universe's ultimate hard drives? Their event horizons storing timelines like files. The math suggests yes, but retrieving that data is another matter. It'd be like trying to reconstruct a burned book from the ashes. For now, the holographic principle remains a radical lens on reality. blurring the line between physics and philosophy. It doesn't just challenge how we see black holes, it forces us to ask whether time itself is a story we've told ourselves, a flickering projection on the edge of an infinite dark. At the tiniest scales of the universe, where spacetime isn't smooth but churns like a bubbling quantum foam, physicists like Carlo Rovelli suggest black holes might not be endpoints at all. They could be cosmic trapdoors collapsing into entirely new baby universes with their own separate timelines. This isn't just wild speculation. Loop quantum gravity, a leading theory attempting to marry Einstein's relativity with quantum mechanics, paints black holes as bridges rather than dead ends. Imagine a dying star's core crunching down not into a singularity, but a tunnel, a quantum gravity shortcut stitching two patches of spacetime together like threads in cosmic fabric. Rovelli's work reveals something astonishing. When a black hole's collapse reaches the smallest possible scale allowed by quantum physics, space can't compress further. Instead, it rebounds, birthing a new universe with its own laws of physics and flow of time. Picture a soap bubble pinching off from a larger one. Our universe's black hole becomes the umbilical cord to an infant cosmos, where time might run faster, slower, or even backward. Some models suggest these baby universes could remain tenuously connected via quantum entanglement, their timelines subtly influencing each other like distant whispers across dimensions. Visualizing this makes your head spin. Spacetime foam, the frothy, ever-shifting quantum landscape at the smallest scales, would writhe like boiling water around the black hole's core. As the tunnel forms, probabilities flicker in and out of existence. One path leads to oblivion, another to a newborn universe. The math hints that these bridges aren't rare flukes but inevitable byproducts of quantum gravity, hidden in every black hole's heart. This opens a dizzying possibility. If we could somehow survive the trip, falling into a black hole might not mean death. It could be a one-way ticket to an entirely new timeline. No grandfather paradoxes, no loops, just a fresh cosmic beginning where time itself operates differently. Of course, the journey would still be fatal by any known physics, and returning to our own universe would be impossible. But the mere idea reshapes our understanding of black holes, from cosmic trash compactors to potential universe factories, where time isn't universal but endlessly inventive. The catch: we'd need a theory of quantum gravity to confirm any of this, something physicists are still racing to crack. Until then, these quantum bridges remain tantalizing shadows in the equations, reminding us that the universe's rulebook might be far stranger than we've dared to dream. Imagine trapping light in a gravitational funhouse where every bounce stretches time itself. That's the bizarre premise of a black hole laser. This theoretical device, straight from the fringes of physics, exploits a phenomenon called superradiance, where light ricocheting between two event horizons doesn't just echo, it amplifies, each reflection growing stronger as it steals energy from the black hole's spin. The result: a cascading signal so distorted by gravity that it could effectively leap backward in time. Recent experiments with analog black holes, created in labs using supercooled atoms or laser pulses, have brought this wild idea closer to reality. Scientists simulate event horizons by manipulating light or sound waves, creating artificial gravity wells where waves slow down as if dragged by a black hole's pull. In one groundbreaking study, researchers observed waves trapped between two simulated horizons, their frequencies shifting dramatically with each pass, a microscopic preview of how a black hole laser might behave. The R-Ziv paper detailing this work even suggests these amplified waves could carry information against time's usual flow, like a shout echoing into the past. Here's how it might work. Picture a pulse of light enters the region between a black hole's outer event horizon and an inner Cauchy horizon, a boundary where predictability breaks down. The light gets caught in a loop, bouncing endlessly while the black hole's rotation pumps energy into it. Each trip through this warped spacetime stretches the light's wavelength, redshifting it into lower frequencies while paradoxically increasing its amplitude. Over countless cycles, the signal could become so time-shifted that it effectively predates its own origin, like a letter arriving before it's mailed. But the universe never makes time travel easy. For this to work, the black hole must be perfectly balanced, a so-called extremal black hole spinning at the maximum possible rate without tearing apart. Even then, quantum effects or instabilities might collapse the laser effect before any meaningful message could be sent, and decoding a time-reversed signal. That's another nightmare. Imagine trying to unscramble a radio broadcast that's been stretched, amplified, and played backward through a cosmic echo chamber. Yet the implications are staggering. If analog experiments can prove the principle, even on a tiny scale, it suggests black holes might naturally broadcast distorted echoes of their own futures into their past. Not quite a time machine, but perhaps a time messenger, hinting that the universe's strict causal order isn't just bendable but breakable. For now, the black hole laser remains a tantalizing what-if, a ghostly whisper at the intersection of relativity and quantum theory. But in labs worldwide, scientists are tuning their instruments, ready to listen for the first crack in time's unyielding wall. What if the spooky link between entangled particles wasn't just quantum weirdness, but a hidden wormhole in disguise? That's the jaw-dropping premise of ER equals EPR, a theory so bold it stitches together two of physics' greatest mysteries. On one side, you have Einstein and Rosen's wormholes, those hypothetical spacetime tunnels abbreviated as ER. On the other, there's Einstein, Podolsky, and Rosen's infamous entanglement paradox, dubbed EPR, where particles mirror each other instantly across any distance, as if sharing a single existence. For decades, these ideas lived in separate corners of physics until Juan Maldacena and Leonard Susskind proposed their two sides of the same cosmic coin. Think of entangled particles like a pair of magic coins, always landing on matching faces no matter how far apart they're flipped. Now imagine those coins aren't just mysteriously linked, they're physically connected by a tunnel too tiny to see, a wormhole threading through the fabric of spacetime. That's ER equals EPR in a nutshell. Every entangled pair might be joined by a microscopic Einstein-Rosen bridge, so minuscule it operates at the Planck scale, far beyond our current ability to observe. The math reveals something staggering. The equations describing entanglement and wormholes are eerily interchangeable, like discovering two languages secretly telling the same story. Scaling this up could rewrite our understanding of black holes. If entanglement creates wormholes, then two black holes formed from the same collapsing star or artificially linked might share a macroscopic bridge through spacetime. Picture two whirlpools in a cosmic ocean, their bases connected by an underwater channel. Fall into one, and you could emerge from the other, not just across space, but potentially across time. Maldacena's work suggests these wormholes wouldn't be the traversable kind seen in sci-fi. They'd be non-traversable, meaning anything trying to pass through would get shredded by quantum chaos. Yet the connection would still exist, a ghostly thread tying black holes together like puppets on strings. This idea gains eerie traction from quantum teleportation experiments, where scientists transmit particle states across labs using entanglement. While not true teleportation, no matter is moved, it proves information can leap between points instantaneously, defying classical limits. If ER equals EPR holds, these quantum leaps might rely on spacetime's hidden geometry, with entangled particles acting as anchors for microscopic wormholes we can't yet see. Some physicists even speculate that spacetime itself could emerge from a vast network of quantum entanglement, like a 3D hologram projected from countless subatomic threads. The implications spiral outward. Could two black holes entangled at birth form a time bridge between distant eras? Might the universe's very structure be woven from these invisible wormhole stitches? For now, the theory remains a thrilling hypothesis, a piece of mathematical origami folding relativity and quantum mechanics into a single shape. But if it's right, the cosmos isn't just interconnected, it's threaded with secret passages waiting to be unmasked. Imagine a structure that doesn't just exist in space but repeats in time, ticking like a cosmic metronome without any energy input. These bizarre objects, dubbed time crystals, sound straight out of a physicist's dream journal, yet they're real, and they might lurk near black hole horizons, acting as nature's most precise timekeepers. First proposed by Nobel laureate Frank Wilczek in 2012, time crystals defy classical physics by breaking time translation symmetry, meaning their atomic patterns oscillate indefinitely without losing energy. Picture a diamond that doesn't just sit on a shelf but pulses in perfect rhythm, its atoms dancing to the universe's hidden beat. Now, drop one of these crystals near a black hole's event horizon where gravity twists spacetime into knots. The extreme tidal forces stretching and compressing everything in reach could sync with the crystal's natural oscillations, creating a feedback loop where time itself starts to echo. Theoretical models suggest these horizon-bound time crystals might stabilize closed time-like curves, those treacherous loops where time folds back on itself. Think of them as cosmic gyroscopes, counteracting the chaotic fluctuations that would normally collapse a time loop before it could form. A black hole's rotation could wind the crystal's structure tighter, forcing it to tick in sync with the warped spacetime around it, like a pendulum swinging in perfect time with a spinning top. But detecting these crystals isn't just hard, it borders on impossible with current technology. Wilczek's original idea faced skepticism until 2017, when researchers used chains of ytterbium ions to create the first lab-grown time crystals. These fragile quantum systems only lasted milliseconds, manipulated with lasers at near absolute zero temperatures. Near a black hole, the conditions would need to be exponentially more extreme. Gravitational forces strong enough to snap neutron stars like twigs, paired with quantum coherence precise enough to maintain the crystal's rhythm. Even if they exist, their signals would likely drown in the roar of Hawking radiation and the violent turbulence of the accretion disk, yet the implications are staggering. If time crystals can form near black holes, they might offer a natural mechanism for time loops, not as flimsy mathematical quirks, but as robust structures woven into spacetime itself. Some physicists speculate they could even serve as time anchors, points where causality locks into place, allowing information to cycle predictably between past and future. Of course, this all hinges on theories we can't yet test, dancing at the edge of known physics. But in a universe where black holes already defy logic, time crystals might be the missing piece, a rhythmic heartbeat in the chaos, ticking toward answers we're only beginning to imagine. Picture holding a rubber band stretched between 2 points. Now imagine that rubber band is space-time, and something invisible is tugging it inward, creating a dent where time itself could pool. That's the eerie power of negative energy, a theoretical form of matter that could make black hole time travel more than just a mathematical curiosity. Unlike the gravity we know, which always pulls, negative energy would push, repelling spacetime like an invisible hand, propping open wormholes or smoothing out the deadly tidal forces near a black hole's core. And one of the strangest places we've glimpsed this phenomenon isn't in deep space, but in a lab, the Casimir effect. Place two metal plates unthinkably close together in a vacuum, and something bizarre happens. Quantum fluctuations between the plates get squeezed out, creating a region of lower energy than the surrounding space. The result, the plates snap together as if pulled by an invisible force. This isn't just a lab trick, it's proof that pockets of negative energy can exist, however fleetingly. Scale this up to cosmic proportions, and you've got the key ingredient for stabilizing a traversable wormhole or even a time-looping black hole geometry. The catch, the Casimir effect produces amounts of negative energy so tiny they're barely detectable. To prop open a human-sized wormhole, you'd need negative energy densities rivaling a neutron star's core, something our universe seems determined to prevent. Enter Miguel Alcubierre's warp drive, another concept leaning on negative energy's power. His 1994 solution to Einstein's equations proposes a spacecraft riding a bubble of warped spacetime, compressed ahead and expanded behind, like a surfer gliding on a wave of distorted reality. The math checks out, but the fuel requirement is apocalyptic. Some estimates suggest you'd need negative energy equivalent to converting Jupiter's entire mass into pure energy. And even if we cracked that, there's another headache. Quantum field theory suggests that large concentrations of negative energy would trigger instabilities, collapsing the warp bubble or wormhole faster than you could say paradox. Why does the universe seem to tease us with these possibilities, only to slam the door? The answer might lie in something called the averaged null energy condition, a cosmic rule of thumb suggesting negative energy can't dominate over large scales or long times. It's as if reality has a failsafe, preventing time travelers from rewriting history willy-nilly. Yet black holes might be the ultimate loophole. Their event horizons already twist the rules, creating regions where negative energy could, in theory, pile up without immediately triggering collapse. Some models even suggest Hawking radiation near a black hole's horizon could generate just enough negative energy to nudge open a microscopic time warp, though harnessing it would be like trying to surf a tsunami with a teaspoon. For now, negative energy remains a tantalizing what-if, a shadow on the edge of physics map. It hints that time travel might not be forbidden by nature, just locked behind a door we haven't found the key to. Until then, black holes keep their secrets close, whispering of possibilities just beyond our reach. When two black holes spiral toward collision, they don't just create gravitational waves, they might rip temporary holes in spacetime itself. Numerical relativity simulations reveal something astonishing. As these cosmic titans merge, their combined rotation could twist the surrounding fabric of reality into knots so tight, they briefly form what physicists call a throat, a tunnel where time and space lose all meaning. Picture two whirlpools merging in a bathtub, their combined vortices sucking water downward into a temporary funnel. Now replace that water with space-time, and you've got a glimpse of how black hole mergers might stitch together portals to other moments in time. LIGO groundbreaking detections of gravitational waves, ripples from colliding black holes, have given us a front-row seat to these cataclysms, but hidden in the data could be clues to something even stranger. As the black holes inspiral, their event horizons stretch and deform like taffy, creating regions where time dilation spikes to extreme levels. For milliseconds, a point near the merger might experience time flowing backward relative to distant observers, like a cosmic glitch in the matrix. Some theorists suggest these fleeting moments could allow quantum information to loop back on itself, imprinting subtle anomalies in the gravitational wave signal, an echo of causality bending under impossible strain. The math behind this is both elegant and terrifying. Numerical models show that during merger, the black hole's combined angular momentum can warp spacetime into a structure called a Cauchy horizon, a boundary where predictability breaks down. Cross this threshold, and equations spit out multiple futures, one where time flows normally, another where it reverses, like a fork in the river of causality. Remarkably, these simulations align with LIGO observations of ring down, the final shudder of the merged black hole settling into its new form. Some analyses detect faint overtones in the signal that don't match standard predictions, hints of extra dimensions or temporal echoes, though skeptics argue these could be noise. Yet even if time rifts exist, exploiting them would require precision beyond anything in nature. The merger's violent chaos would shred any object approaching the throat, and the portal's lifespan would be shorter than a quantum fluctuation. But here's the tantalizing twist. If advanced civilizations could somehow trigger controlled black hole mergers, say, by steering smaller black holes into collision, they might engineer microscopic time loops. Imagine a civilization firing black holes like bullets into a cosmic bullseye, each collision opening a nanosecond window to send data backward, far-fetched. Absolutely, but in a universe where gravity can bend time, the line between impossibility and ingenuity blurs with every gravitational wave we detect. For now, these ideas linger at the edge of physics, waiting for LEGO's next big catch, a merger so bizarre, it forces us to rewrite the rules. Until then, black hole collisions remain both a spectacle of destruction and a siren song, whispering that time's grip might not be as unbreakable as we think. Roger Penrose once argued that the universe has a built-in safety feature, a cosmic referee blowing the whistle whenever physics threatens to spiral into nonsense. His strong cosmic censorship conjecture claims that every singularity, those infinitely dense, physics-breaking cores of black holes, must be hidden behind an event horizon forever cut off from our universe. No naked singularities allowed. It's nature's way of keeping causality from unraveling, ensuring that whatever madness happens inside a black hole stays inside, like locking chaos in a basement. But here's the twist. Penrose himself once played with fire, exploring the possibility of bare singularities, one so exposed they could rewrite time itself. Picture a singularity not cloaked by an event horizon but hanging in space like a raw nerve. These hypothetical, naked singularities would be gravitational anarchists bending spacetime with no rules to restrain them. Without an event horizon to shield the universe from their infinite curvature, nearby observers might witness time snapping backward or splitting into branches, like a broken record skipping between decades. Conformal diagrams, those intricate maps of spacetime, show naked singularities as jagged edges where the grid of reality simply ends. No smooth paths forward, just a tangle of broken trajectories where particles could, in theory, loop back on their own histories. The irony is delicious. The same Penrose who gave us cosmic censorship also discovered that colliding gravitational waves could, under perfect conditions, forge a naked singularity. It's as if the universe whispered a secret in his ear, then promptly denied it. General relativity allows these anomalies, but quantum effects likely swoop in like cosmic bouncers, cloaking them behind horizons at the last second. The math teases us with possibilities. A spinning black hole slowed to near halt by external forces might expose its central singularity, or a supermassive black hole's collapse could leave behind a naked core. Yet if one did exist, the implications would rewrite physics. A naked singularity could serve as a time machine with no off switch, no event horizon to stop you from tweaking the past and unleashing paradoxes like an overeager time tourist. Radiation from its surface wouldn't redshift into obscurity like Hawking radiation. It'd blast outward, carrying distorted signals from the end of time. Some models even suggest these freaks of nature could emit precursor particles that arrive before they're emitted, like a letter dated yesterday arriving tomorrow. Penrose's censorship hypothesis remains unproven, hanging over physics like a guillotine. If it holds, time travel via singularities is doomed by cosmic law. If it fails, the universe might be far wilder than we dreamed, a place where time's arrow isn't just bendable but breakable, waiting for the right gravitational storm to crack it open. For now, naked singularities linger in the equations, taunting us with what almost could be. Crossing a black hole's event horizon should feel like floating into darkness, gentle, uneventful, the laws of physics lulling you toward oblivion. At least that's what Einstein's equations suggest, but in 2012, a group of physicists dropped a bombshell. What if the horizon isn't a silent threshold but a raging inferno? The firewall paradox, born from the minds of Olmary, Marolf, Pulczynski, and Sully, collectively known as AMPS, turns black hole time travel from a thought experiment into a suicide mission. Imagine stepping toward a horizon, only to hit an invisible wall of ultra-high-energy particles, incinerating you before you even notice. This nightmare scenario stems from a cosmic tug-of-war between two sacred principles of physics: Einstein's smooth spacetime and quantum mechanics' unbreakable rule that information can never be destroyed. When matter falls into a black hole, quantum theory insists its information must somehow escape, perhaps encoded in Hawking radiation. But here's the snag: for that information to stay consistent, the radiation emitted early must be entangled with radiation emitted late, a delicate quantum handshake spanning the black hole's lifespan. Yet, if nothing special happens at the horizon, if it's truly no drama, as relativity claims, then late radiation must also be entangled with the infalling matter. That's a quantum impossibility. You can't entangle one thing with two others simultaneously without breaking the math. The solution: a firewall, a boundary so violent it severs these forbidden connections, roasting anything that dares approach. The implications for time travel are grim. If firewalls exist, any attempt to exploit a black hole's time-bending properties would end in vaporized atoms. Want to orbit near the horizon to leap forward in time? The firewall ensures you'd arrive as scattered plasma, hoping to dive through a wormhole's throat. It's now lined with particle accelerators hotter than a supernova. Even sending a probe becomes futile; its data would disintegrate before transmission. Not everyone buys the firewall's lethality. Some theorists argue it violates the equivalence principle, the cornerstone of general relativity guaranteeing free fall feels weightless. Others propose gentler fixes like quantum hair subtle imprints on the horizon that preserve information without the blaze. But the debate rages on, exposing a deeper truth. Black holes might be the universe's ultimate riddles, hiding their secrets behind layers of paradox. For now, firewalls stand as a brutal reminder time's corridors may exist, but nature could have rigged them with traps. Black holes don't always announce themselves with blazing accretion disks or voracious appetites for stars. Some might lurk in the cosmic shadows, invisible and undetectable primordial black holes forged not from collapsing stars, but from dense knots of dark matter in the universe's infancy. These hypothetical relics, smaller than an atom yet heavier than a mountain, could be drifting through our galaxy right now, warping time in their wake like silent chrono-vandals. Imagine a black hole so tiny it slips between atoms without a trace, yet its gravitational grip is so fierce, it twists the flow of time around it like a wrung-out towel. Theorists suggest these dark matter black holes could form through mechanisms stranger than stellar collapse. In the early universe, fluctuations in the density of dark matter, the invisible glue holding galaxies together, might have birthed micro-black holes directly, bypassing the need for stars entirely. Unlike their stellar counterparts, these wouldn't emit Hawking radiation detectable by our telescopes. They'd be cloaked in darkness, their presence betrayed only by subtle distortions in spacetime. Pass near one, and you might not even notice until you check your watch and realize hours have vanished in what felt like seconds, or vice versa. What makes these objects potential time gates is their stealth. Without the violent interactions of regular black holes, their event horizons could exist as pristine, undisturbed time warps. Some models suggest clusters of primordial black holes might create localized pockets where time flows at different rates, like eddies in a river. A ship passing through such a region could emerge into the future or past relative to the outside world, with no telltale radiation or debris to mark its passage. It's time travel without the fireworks, no glowing wormholes, no screaming accretion disks, just the quiet, inexorable pull of gravity doing its work unnoticed. But the real mind bender, these black holes might not just bend time, they could stitch it. If dark matter interacts with spacetime differently than ordinary matter, as some theories propose, their singularities might form natural bridges between eras. Picture a network of these microscopic time gates scattered through the cosmos, a hidden subway system where the stations are moments in history. The catch: finding one without light or heat to give them away, the only signature might be an anomalous time delay in signals from distant stars, like a cosmic stopwatch running slightly fast or slow for no apparent reason. For now, primordial dark matter black holes remain ghosts in the equations, their existence hovering between theory and speculation. But if they're out there, hiding in the voids between stars, they could be the universe's most elegant time machines, proof that the greatest mysteries don't always roar. Sometimes they whisper. At the quantum level, reality behaves like a cosmic game of chance, where particles vanish and reappear in impossible places, as if the universe itself rolls dice. Now apply that logic to a black hole's singularity, the point where gravity becomes infinite and spacetime shatters. What if particles falling in don't just vanish, but quantum tunnel through the singularity, popping out somewhere or someone entirely unexpected? This isn't just speculation. Hawking's concept of space-time foam suggests that at the tiniest scales, the fabric of reality isn't smooth but churns with microscopic wormholes and quantum fluctuations, bubbling like a boiling pot. In this chaotic froth, particles might bypass the crushing grip of a singularity entirely, tunneling into alternate timelines like ghosts slipping through walls. Picture this: an electron plunges toward a black hole's heart, where classical physics says it's doomed to smash into the singularity, but quantum mechanics offers a sneaky escape. There's always a non-zero chance, however faint, that the electron could teleport past the singularity, reappearing in another universe or even another moment in time. Hawking's foam theory takes this further, proposing that these quantum jumps wouldn't be neat or predictable. Instead, they'd be random, chaotic hops, like a cosmic game of musical chairs where the seats are scattered across different eras. One particle might emerge a second before it entered, another might land a million years in the past. The math behind this is fiendishly complex, but experiments with quantum tunneling in labs give us clues. We already know particles can barrier hop in ways that defy classical physics: electrons teleporting through solid walls, photons appearing on the far side of impassable energy barriers. Scale that up to a black hole, and the barriers aren't just energy thresholds, they're the twisted wrecks of spacetime itself. Some models suggest the singularity might act like a quantum scrambler, shredding particles into their fundamental bits before reassembling them in another timeline, like a cosmic fax machine sending data through the static of the void. But here's the catch: these jumps would be utterly uncontrollable. Without a way to steer the tunneling process, any time leap would be a one-way ticket to randomness. You might re-emerge in the Cretaceous period, the far future, or a parallel reality where gravity works backward. Hawking himself wrestled with this, arguing that quantum foam's chaos would prevent any coherent time travel, nature's way of keeping paradoxes at bay. Yet the possibility lingers, dangling at the edge of known physics. If even a single particle could tunnel through a black hole's heart and survive, it's proof that time's grip isn't just flexible, it's full of holes. For now, this remains a ghostly whisper in the equations, a might-have-been that tantalizes theorists. But in a universe where quantum rules let particles be in two places at once, who's to say time travel isn't just another roll of the cosmic dice? What if every black hole is secretly recording the universe like a cosmic security camera? Physicist Gerard T. Hooft proposed something even wilder: that the event horizon doesn't just trap matter, it etches history into its surface like grooves on a vinyl record. Picture a black hole not as a cosmic trash compactor, but as the universe's ultimate DVR, storing every particle that ever crossed its boundary in flickering pixels of quantum information. This holographic principle suggests the third dimension we experience might just be an illusion, a projection from a two-dimensional surface humming with encoded data. And if that's true, could an advanced civilization rewind the tape? Think of how a DVD encodes an entire movie into microscopic pits on its surface. A black hole's horizon operates similarly, except instead of storing light and sound, it captures events. When a star or spacecraft falls in, its information gets smeared across the horizon in Planck-scale bits, a process called pixelation, where the third dimension collapses into a hologram. T. Hooft argues this data isn't lost, just rewritten in a language we don't yet understand. Theoretically, if you could scan the horizon with Planck-level precision, something no technology today even approaches, you might reconstruct the star's final moments, or even the faces of long-dead astronauts, like forensic analysts dusting for fingerprints on the edge of oblivion. But decoding this cosmic hard drive isn't as simple as hitting play. The hologram is scrambled by chaotic quantum interactions, like a shattered mirror reflecting 1,000 fractured timelines. Some models suggest black holes use error-correcting codes similar to those in quantum computers, meaning the data is there, just buried under layers of encryption. A civilization advanced enough to crack it wouldn't just be reading history, they'd be editing reality itself. Imagine tweaking a single bit on the horizon to change how a particle fell in 1 billion years ago, like editing a single frame in a movie and altering the entire plot. The catch: thermodynamics might have the final say. Even if we could extract the data, entropy dictates that playing it backward would require reversing the universe's arrow of time locally, a feat akin to unscrambling an egg atom by atom. Yet black holes already defy classical thermodynamics, whispering that the rules might bend in their shadow. For now, holographic time records remain locked behind physics we've barely glimpsed, a reminder that the universe's past might not be gone, just waiting to be rewound. The Event Horizon Telescope didn't just capture the first image of a black hole. It might have accidentally photographed a time machine in action, that haunting ring of light around M87's shadow. It's not just bent space, it could be folded time. Einstein predicted that black holes warp light so severely they act like cosmic lenses, distorting distant stars into smeared halos. But reality might be stranger. Near the event horizon, gravity twists spacetime so violently that photons don't just curve, they loop. Some light orbits the black hole multiple times before escaping, creating eerie photon rings in the telescope's images. Here's the twist: those rings aren't just spatial artifacts, they're temporal ones. Every extra loop a photon takes around the black hole means it spent additional time in that gravitational whirlpool. By the time it reaches our telescopes, its journey could span years, decades, or even centuries longer than light arriving directly. This means the inner rings of the black hole's shadow might contain layered snapshots of the same event, like a cosmic flipbook. Imagine a star exploding near M87 500 years ago. Its light would reach us directly first, but some photons would take the scenic route, swirling around the black hole before breaking free. Those delayed photons could arrive today, superimposing the ancient explosion onto our modern observations. The result: a single image that shows the same cataclysm at multiple points in its own timeline, like watching a supernova's birth, peak, and fade simultaneously in one ghostly frame. Scientists call this effect time lensing, and it's not just theoretical. Simulations of the Event Horizon Telescope's data reveal subtle anomalies, repeated patterns in the photon rings that match predictions of light echoing from different eras. It's as if the black hole's shadow isn't just a dark spot, but a hall of mirrors reflecting disjointed moments. The precision needed to untangle these time-folded signals is staggering, requiring algorithms that can distinguish between light from the Roman Empire's height and light emitted last Tuesday. Yet if we could decode these layers, black hole shadows might become windows into the past. No need for a time machine, just a telescope sharp enough to read the universe's natural archives etched into bent starlight. The implications are dizzying. A civilization advanced enough to map these photon rings could reconstruct cosmic history passively, watching dinosaur-killing asteroids strike or ancient stars ignite by studying the light trapped in black hole orbits. Of course, the universe loves a catch. The same extreme gravity that bends time also scrambles these signals beyond recognition. Untangling a single event's multiple ghosts would be like reconstructing a symphony from an orchestra playing every note at once. But with next-generation telescopes and AI-trained models, we might one day isolate these whispers from the void, proof that the past isn't gone. It's just orbiting in the dark, waiting to be seen again. Imagine encoding humanity's greatest knowledge, every book, song, and scientific breakthrough into an indestructible probe and hurling it toward Sagittarius A, the supermassive black hole at our galaxy's heart. Not to destroy it, but to preserve it across millennia. The same gravity that makes black holes cosmic shredders could also transform them into the ultimate time vaults, slowing the probe's clock so drastically that what feels like hours inside the gravity well could equate to millions of years passing on Earth. This isn't just poetic speculation, it's a survival strategy straight from Einstein's playbook. Let's crunch the numbers. Sagittarius weighs roughly 4 million times our Sun's mass, creating a gravitational time dilation effect so extreme that near its event horizon, time crawls to a near halt relative to the outside universe. For a probe orbiting just outside the point of no return, the math suggests one Earth year could stretch into thousands for those aboard, or more radically, a single minute for the probe might equal decades for us. Scale this up, and a message deposited today could re-emerge from the probe's perspective in what feels like weeks, while Earth civilizations rise and fall in its absence. The catch, retrieving the data, would require surviving forces that stretch atoms like taffy and radiation blasts brighter than 1 trillion suns. But here's where quantum tricks might help. Instead of sending physical objects, we could encode information in particles theoretically immune to spaghettification, quantum dots or light pulses locked in superposition, bouncing just outside the horizon like a photon skipping rope. Recent studies on quantum buoyancy suggest certain states of matter might resist tidal disruption long enough to exploit time dilation without crossing into oblivion. Picture a laser signal fired into the black hole's ergosphere, the region where spacetime itself gets dragged around the hole's spin. The signal's frequency would redshift into near nothingness as it struggles against gravity, but its quantum signature could persist, re-emerging billions of years later when the black hole evaporates via Hawking radiation, our message etched into the very fabric of its dying breath. Of course, the universe loves a paradox. Any data preserved this way would face the observer problem. If time near the black hole flows slower, the message might return to an unrecognizable future where humanity's descendants or alien civilizations lack the keys to decode it. It's like mailing a letter in a language no one speaks, addressed to a country that no longer exists. Yet the audacity of the idea lingers. Black holes might not just bend time, they could be the universe's ultimate archivists, holding memories of lost eras in their gravitational grasp until the stars themselves grow cold. What if every black hole in our universe isn't an endpoint, but a bridge to another reality entirely? This is the spine-tingling premise of multiverse black hole bridges, where cosmic monstrosities we think of as destructive might actually be gateways to worlds with entirely different flows of time. Max Tegmark's framework splits the multiverse into 4 mind-bending levels, and black holes could be the linchpin connecting them. At level 1, we've got infinite universes with the same physics as ours, just rearranged, like cosmic copies of Earth where dinosaurs never went extinct. But level 2, that's where things get wild. Here, universes bubble off from one another like boiling water, each with its own unique laws of physics. And black holes might be the needles stitching these cosmic patches together. Picture a black hole's singularity not as a dead end, but as a cosmic sewing machine, punching through the fabric of spacetime to knot our universe to another. The equations of general relativity don't forbid this, they simply shrug and say, maybe. In some models, the infinite density at a singularity doesn't crush matter into oblivion. Instead, it warps spacetime so violently that it pinches off into a new universe, like a soap bubble splitting in midair. This infant universe would inherit its parents' energy, but could evolve entirely different constants. Gravity might be weaker, light slower, or time itself could flow backward. Tegmark's Level 2 suggests these baby universes are everywhere, nested inside black holes like Russian dolls hidden in the dark. Now layer in the many worlds interpretation of quantum mechanics, where every decision forks reality into alternate timelines. Normally, these branches exist in abstract Hilbert space, a mathematical playground, but what if black holes physically anchor them? Imagine a particle teetering on the edge of a quantum decision, to spin left or right. Many worlds says both outcomes happen, splitting reality. Now toss that particle into a black hole. Some theories suggest the singularity could resolve the superposition by ejecting each possibility into a separate universe. The left spin version of you emerges in one timeline, the right spin version in another. The black hole isn't destroying information, it's redistributing it across the multiverse like a cosmic switchboard operator. The implications for time travel are staggering. If black holes link to universes with different time axes, crossing one might not just move you through space, it could hurl you into a reality where time runs sideways. Picture a universe where entropy decreases by default, making broken cups leap back onto tables and dead stars reignite, or one where time is a two-dimensional plane, letting you traverse eras like navigating a map. The catch: these bridges likely only work one way. Once you've crossed, the extreme warping of spacetime would prevent return trips, stranding you in an alien timeline with no way to phone home. Yet here's the tantalizing wrinkle: quantum entanglement might offer a lifeline. If particles in connected universes remain entangled, changes in one could instantly affect the other, like twins separated at birth still feeling each other's pain. Some models suggest advanced civilizations could exploit this to send signals, or even matter, through black hole bridges by manipulating entangled particles. It's less a time machine and more a quantum pony express, racing messages across the multiverse's tangled web. Of course, the universe loves a paradox. If black holes truly are multiverse conduits, why haven't we detected strange radiation or anomalies from other timelines leaking into ours? Some theorists argue we might have cosmic rays with inexplicable energies or particles that behave as if they remember futures that never happened. Others counter that the sheer scale of these bridges makes them indistinguishable from noise, like trying to hear a whisper in a hurricane. For now, multiverse black hole bridges remain at the edge of plausibility, a dazzling intersection of general relativity, quantum mechanics, and pure imagination. They hint that the cosmos might be more interconnected than we dreamed, with black holes serving not as tombs, but as crossroads where all possible times and realities collide. What if the only way to survive a black hole is through the ultimate cosmic gamble, a game where the stakes are existence itself? The quantum suicide thought experiment takes Schrödinger's famous cat to a terrifying extreme. Imagine pointing a gun at your head rigged to a quantum trigger where the particle's random decay decides whether it fires. In a universe where every quantum possibility branches into alternate timelines, you'd only ever experience the realities where the gun doesn't fire, because in the ones where it does, you're not around to observe it. Now replace the gun with a black hole's event horizon. Plunge in, and quantum mechanics suggests you might always survive, at least from your own perspective, because every possible outcome where you perish branches away, leaving only the timelines where you improbably cheat death. This isn't just philosophical sleight of hand. Tie it to the Boltzmann brain paradox, which asks why we don't find conscious observers randomly spawning from quantum fluctuations in the void. If the universe tends toward entropy, shouldn't disembodied minds flicker into existence more often than whole civilizations? The eerie answer: maybe they do, but like our quantum suicide survivor, they're the only ones around to notice. Near a black hole where space-time and probability twist into knots, these paradoxes collide. An observer falling in might experience infinite branching realities, each escape statistically absurd, a 1 in a trillion fluke where tidal forces miraculously miss vital atoms or Hawking radiation conspires to cushion their descent. Yet statistically, there's always a branch where they persist, their consciousness clinging to existence like a cosmic final girl in a horror movie with endless sequels. The implications ripple outward. If consciousness really does anchor reality, a notion flirted with in quantum interpretations like von Neumann-Wigner, then a black hole might be less a physical obstacle and more a quantum filter. Every moment of survival reshuffles the deck, spawning new universes where the observer's continuity feels unbroken, even as their body is torn apart in countless others. It's immortality through multiplicity, with the black hole acting as a grisly prism, splitting you into endless variations, some spaghettified, some teleported, some merged with the singularity's heart. Critics argue this reduces physics to solipsism, where reality bends to the observer's whim. But black holes already defy intuition. Why wouldn't they twist identity itself? Perhaps the true horror isn't dying in a singularity, but realizing you can't because quantum mechanics keeps dealing fresh hands from a deck with infinite aces. The universe might not care which version of you survives, only that at least one always does, locked in a cosmic game where the house never loses. Picture a future where black holes aren't just cosmic oddities, they're tourist attractions. Vacationers from advanced civilizations might one day flock to primordial black holes, those ancient relics drifting unseen through the galaxy, not just to witness their time-bending effects, but to exploit them. A family could snap a selfie near the event horizon, their smiles stretched across centuries as they experience minutes while millennia pass back home. But this whimsical scenario hides a darker twist. Every interaction, every probe sent or energy harvested, could nudge these delicate time machines toward instability, altering their evolution in ways that ripple unpredictably across history. This is the black hole time tourism paradox, a blend of chaos theory and cosmic vandalism. Primordial black holes are fragile time capsules, their mass and spin finely tuned by eons of isolation. Even minor disturbances, like a sightseer's ship emitting waste heat or a gravity wave from a passing starship, could shift their trajectories or hasten their evaporation through Hawking radiation. Over millennia, cumulative visits might destabilize the very time loops that drew tourists in the first place, erasing the attractions future travelers came to see. It's like a medieval village paving over its own ruins to build souvenir shops, except here, the ruins are the fabric of causality itself, the real enigma. We see no evidence of this meddling. If black hole tourism were rampant, primordial holes should show signs of tampering, unusual spin rates, unexpected decay patterns, or even missing entirely from regions where calculations predict they should lurk. Their undisturbed silence hints at something called the anthropic shadow, a cosmic version of the observer effect where the absence of proof becomes proof itself. Perhaps civilizations smart enough to manipulate black holes are also wise enough to avoid it, recognizing the butterfly effect of even a single photon out of place. Or worse, maybe every civilization that ever tried it erased itself from history, its timeline collapsing under the weight of paradoxes. One terrifying model suggests that time tampering could spawn self-correcting feedback loops where alterations to the past recursively erase the very tourists who made them. Imagine a traveler nudging a black hole's path, inadvertently preventing their own ancestors from evolving, a grandfather paradox played out on a galactic scale. The universe might resolve this by pruning entire branches of reality, leaving only the untouched timelines where no one ever interfered. In this light, the pristine quiet of primordial black holes isn't just a mystery, It could be a gravestone marking where countless futures tried and failed to rewrite time. Yet the silence also offers hope. If black holes remain unspoiled, it might mean the universe enforces a cosmic conservation law, locking time's arrow in place with quantum checks and balances. Or perhaps we're simply the pioneers who will one day leave the first footprints on the shores of causality, staring into the abyss and finding for once that it doesn't stare back. Could the swirling chaos inside a black hole actually be running calculations more complex than all the supercomputers on Earth combined? Seth Lloyd, a pioneer in quantum computing, proposed something downright cosmic. Black holes might be nature's ultimate processors, crunching quantum data at scales that make our most advanced machines look like abacuses. The math behind this is staggering. Every particle falling into a black hole doesn't just vanish. It adds to an immense, chaotic computation where the singularity isn't a dead end but a processor rewriting reality itself. And if that's true, the implications for time travel aren't just theoretical, they're coded into the universe's operating system. Think of a black hole as a quantum computer with infinite RAM. Lloyd's work suggests the event horizon acts like a cosmic hard drive, encoding information in Planck-sized pixels, each one a qubit in the universe's most powerful processor. As matter crosses the horizon, its quantum states get entangled, scrambled, and reprocessed in ways that could simulate alternate timelines. Picture a black hole not as a destroyer, but as a render farm for parallel realities, where every possible outcome of every quantum decision gets calculated simultaneously. The mind-bending part, those simulations might not stay trapped inside. Hawking radiation, the faint glow escaping black holes, could carry fragments of those computations back into our universe, like echoes of futures that never were. The time travel twist comes from how quantum computations handle causality. In a lab, quantum particles can briefly time travel by exploiting entanglement to influence past states, a phenomenon called retrocausality. Scale that up to a black hole's processing power, and entire timelines could be folded into the calculation. Imagine a civilization encoding a message into the quantum states of particles and feeding them into a black hole. The singularity's computation might tweak those states retroactively, altering the message before it was even sent, a literal rewrite of history powered by gravity's grindstone. Critics argue this stretches quantum theory to breaking point, yet recent analog experiments with black hole lasers in labs show how quantum systems can mimic event horizons, complete with simulated Hawking radiation. If we can recreate these effects on a tabletop, who's to say the universe hasn't built the real thing? The eerie silence from primordial black holes, those hypothetical relics from the Big Bang, might even hint at something stranger. If they're cold and dormant, their computations could be running on cosmic background radiation, simulating timelines where humanity never arose. The ultimate question isn't whether black holes can compute, but what they're calculating. Are they merely crunching quantum probabilities or actively rendering alternate versions of us right now? If the latter, time travel might not require a machine, just a way to hack the universe's source code, written in gravity and spinning behind the curtain of the event horizon. Until then, black holes keep their secrets locked behind layers of paradox, their processors humming in the dark. Inside a black hole, the rules of reality don't just bend, they shatter. One of the most radical theories in physics suggests that within the event horizon, time and space swap roles entirely. What we experience as the unrelenting forward march of time becomes just another direction you can move through, like walking left or right. Meanwhile, the dimension we think of as depth transforms into something stranger, a one-way corridor where the singularity isn't a place but an inevitable future. This flip isn't science fiction, it's baked into Einstein's equations. When you cross the horizon, the signs in the math literally switch, turning time into space and space into time. The result, a realm where you could theoretically stroll through moments like browsing shelves in a library, with each step taking you deeper into someone else's yesterday or tomorrow. String theory offers an eerie parallel to this dimensional swap. In certain models, extraspatial dimensions, usually curled up into unfathomably tiny loops, can unfurl under extreme conditions, revealing hidden directions of movement. Picture a garden hose. From a distance, it looks like a simple line, but zoom in, and you'll find an entire circle wrapped around its length. Near a black hole's singularity, something similar might happen to time itself. The dimension we perceive as linear could unravel into a labyrinth of branching paths, where moving forward through space actually carries you backward through time, or sideways into alternate versions of the same event. This gets even stranger when you consider how gravity behaves inside the horizon. Outside, gravity pulls you toward the black hole's center, a point in space. But once you're inside, that pull no longer points somewhere but someone. The singularity isn't just crushing you, it's waiting for you, as inevitable as next Tuesday. Every path leads toward it, not because space is collapsing, but because time itself is funneling you toward a final moment. To escape, you wouldn't need to outrun gravity, you'd need to outrun the flow of time. Imagine navigating this topsy-turvy world. A clock tied to your wrist wouldn't tick steadily forward. It might spin wildly or freeze altogether depending on which time direction you faced. Light emitted from your flashlight could curve back toward you, not because of gravity, but because the future is literally pulling it in. Even your own biology would warp in ways that defy intuition. Your cells aging backward as you move through the horizon's twisted geometry, or your memories unraveling as you strayed too close to a temporal eddy. The implications for time travel are dizzying. If time is a spatial dimension inside a black hole, changing your when could be as simple as turning a corner. Want to revisit last week? Take a left at the singularity's shadow. Need to skip ahead a century? Follow the right-hand spiral. Of course, the universe has safeguards. The same forces that make this possible would also scramble any coherent journey, stretching your atoms across eons or fracturing your consciousness into infinite copies. You might technically arrive in the past, but you'd be less a time traveler and more a ghost, your existence smeared across moments like ink in water. Yet the math insists this isn't fantasy. Black holes don't just bend time, they rewrite its very definition, proving that our familiar arrow of time is just a local custom in a far weirder cosmic neighborhood. Whether we'll ever decode these rules or survive the attempt remains one of physics' greatest open questions. For now, these inverted dimensions exist only in equations and dreams, a reminder that the universe's strangest truths often lurk just beyond the edge of comprehension. When LIGO detected gravitational waves from colliding black holes, scientists expected a clean signal, a ripple that rises, peaks, and fades. But buried in the data was something peculiar, faint, repeating echoes trailing the main event like a cosmic déjà vu. These whispers could be glitches in the detectors, or they might be evidence of spacetime itself folding back on itself near the black hole's horizons, creating microscopic time loops that bounce gravitational whispers into the past. The math behind this is as elegant as it is radical. When two black holes merge, their event horizons stretch and vibrate like drumheads, producing gravitational waves. Normally, these waves escape outward, never to return. But if quantum gravity effects near the horizon create even a partial barrier, a firewall or exotic matter, some waves could reflect back, colliding with incoming waves in a feedback loop. Picture shouting into a canyon where your voice returns seconds later, slightly distorted. Now imagine that canyon is time itself, and your voice is a ripple in the fabric of reality. These echoes would carry subtle fingerprints of their journey, stretched and redshifted from looping through warped spacetime. Critics argue these echoes are mere noise vibrations in LIGO mirrors or artifacts of data processing. But a 2019 study led by physicist Nayesha Shorty analyzed hundreds of collisions and found echo signals aligning with predictions of quantum naked singularities, where time loops could form briefly before quantum effects cloaked them again. The timing was eerie. Echoes appeared roughly the time it would take light to circle the black hole's diameter, a hallmark of spacetime folding back on itself. Skeptics countered with Occam's razor, why invoke exotic physics when mundane explanations suffice? Yet 2021 reanalysis using AI noise filtering techniques found the echoes persisted, their patterns stubbornly consistent across multiple events. The debate hinges on a deeper question: does space-time remember its own distortions? If black hole horizons act like cosmic echo chambers, they might not just trap matter, they could trap moments, replaying fragments of the past like a scratched record. Recent analog experiments with fluidic horizons in water tanks have recreated similar echo patterns, suggesting the phenomenon isn't purely mathematical. But the ultimate test may come from LISA, the space-based gravitational wave detector launching in the 2030s. Free from Earth seismic noise, it could catch these whispers with crystal clarity, revealing whether time loops are hidden in plain sight or if we've been chasing cosmic mirages all along. Either way, the echoes hint at a universe far stranger than we imagined, one where even the most destructive events might leave ghostly traces, reverberating through time long after the black holes themselves have faded to silence. What if time near a black hole doesn't just bend, it listens? John Wheeler, the physicist who coined the term black hole, once proposed a radical idea: the universe isn't just something we observe, it's something we participate in. At the quantum level, particles don't have definite states until they're measured, as if reality itself waits for a conscious observer to make choices. Now crank that up to cosmic scales near a black hole's event horizon, where gravity warps not just space but the very fabric of causality. Could consciousness, the act of observation, play a role in shaping how time flows in these extreme environments? Picture a meditator sitting near the boundary of a black hole, their mind focused inward. In our everyday world, time feels linear, ticking forward like a metronome. But under the black hole's gravitational spell, that rhythm distorts. Minutes could stretch into years or collapse into seconds. Now layer in Wheeler's participatory principle. What if the meditator's focused awareness alters the probabilities around them, subtly nudging quantum states in ways that amplify time dilation? It's not magic, it's the quantum observer effect scaled to cosmic proportions. Just as Schrödinger's cat exists in a superposition until someone opens the box, time near the horizon might remain fluid until consciousness collapses it into a definite flow. This isn't just philosophical musing. Psychedelic experiences offer eerie parallels. Users of substances like DMT or psilocybin often report losing all sense of time, describing moments that feel like eternities or entire lifetimes compressed into breaths. Neurologically, these drugs disrupt the brain's default mode network, the system that stitches our perception of time into a coherent narrative. Near a black hole, gravity might do something similar, stretching neural processes to the point where subjective time shatters entirely. Could these altered states be microscopic echoes of the time-warping effects near a singularity? Some theorists suggest that extreme gravity and psychedelics might both unlock the brain's latent ability to perceive non-linear time, like tuning a radio to frequencies normally drowned out by reality's noise. The implications spiral outward. If consciousness interacts with time's fabric, could advanced civilizations use focused thought to stabilize time loops or navigate black hole portals? Ancient mystics claimed enlightenment allowed them to step outside time. Perhaps they were intuiting truths physics is only now glimpsing. Even if this sounds esoteric, the math hints at connections. Quantum entanglement shows particles influencing each other instantaneously across distances, defying classical time. If consciousness arises from quantum processes in the brain, as some models propose, why couldn't it resonate with time's elasticity near a black hole? Of course, skeptics dismiss this as anthropic fantasy, assigning cosmic significance to human perception. Yet the universe keeps surprising us. Black holes already defy intuition. Why wouldn't they also defy the assumed divide between mind and cosmos? Whether consciousness shapes time or merely rides its currents, one thing's certain: near a singularity, all bets are off. The observer isn't just watching the clock, they might be winding it. There's a moment in every black hole's life when the impossible becomes inevitable, when the crushing weight of its own gravity collapses the singularity not into nothingness but into everythingness. Imagine the ultimate cosmic reset button, a point so infinitely dense, so incomprehensibly hot that it doesn't just bend time, it snaps it like a twig, triggering a new Big Bang. This isn't science fiction. It's the heart of the black hole finale paradox, a theory suggesting that every singularity might be a cosmic phoenix, dying in fire only to birth an entirely new universe from its ashes. Roger Penrose's conformal cyclic cosmology paints this breathtaking picture. In his model, our universe's distant future, where black holes dominate and even protons decay, eventually stretches spacetime so thin that all distances and energies reset to near zero. The universe becomes indistinguishable from its own birth conditions, effectively looping back to a new Big Bang. Black holes, in this view, aren't dead ends. They're cosmic incubators, their singularities acting as seeds for fresh realities where time itself reboots. Picture a Russian nesting doll of universes, each black hole death spawning an entire cosmos inside its corpse, complete with its own arrow of time and physical laws. But here's the time travel twist. If black holes truly are Genesis engines, could information or even consciousness survive the transition? Quantum gravity theories suggest that the singularity's infinite curvature might not obliterate information, but reprocess it, like a cosmic 3D printer melting down old blueprints to forge new ones. Hypothetical survivors falling into such a singularity wouldn't just travel through time, they'd transcend it entirely, emerging in a newborn universe where their very atoms become the building blocks of new galaxies. The catch: this rebooted reality might operate under completely different physics. Time could flow backward or in loops, or not exist as we know it at all. The math gets wilder when you consider Kerr black holes, those spinning monstrosities with ring-shaped singularities. Their rotation could twist spacetime so violently that the Big Bang reset isn't just a one-time event but a continuous cycle. Picture a washing machine on spin cycle, endlessly churning out new universes with every rotation. In this scenario, time travel isn't a technological feat, it's baked into the cosmos's DNA. Want to visit the past, wait for the next cosmic iteration, and hope the new universe's laws allow it? Of course, nature loves a paradox. If black holes truly birth universes, does that mean our own cosmos could be the offspring of some long-dead Leviathan's collapse? And if so, are the constants of our reality, the speed of light, the strength of gravity, just inherited quirks from that ancestral singularity? It's a dizzying thought. Every black hole we see might not just warp time locally, but host entire timelines inside them, nested like layers in an onion. Yet the most haunting question remains: if time truly resets at singularities, does that render all time travel futile? Any changes made in one cycle would vanish with the next Big Bang, like writing on a chalkboard erased between classes. Or worse, could meddling with a black hole's interior alter the laws of its offspring universe, making us unwitting gods of realities we'll never see? The universe keeps its tightest secrets locked behind the event horizon's veil, leaving us to wonder whether time's arrow is a straight line, a loop, or something far stranger, a spark jumping between cosmic kindling, forever reigniting. From spinning black holes that twist time into loops to wormholes acting as cosmic shortcuts between eras, we've journeyed through some of the most mind-bending theories linking black holes and time travel. We've seen how a dying star's collapse might birth an entirely new universe inside its singularity, how quantum entanglement could stitch hidden wormholes between particles, and how even the faint echoes of colliding black holes might carry whispers from the past. Each theory pushes the boundaries of physics, turning science fiction into tantalizing possibility. But here's the real kicker. Every one of these ideas stems from real math, from equations scrawled on blackboards by some of the brightest minds in history. Black holes don't just warp space, they shatter our intuition, proving time isn't the rigid, unbreakable arrow we thought. It's more like a river with whirlpools and eddies where the current might even reverse. Whether it's Hawking radiation encoding the past, white holes spewing out alternate futures, or the holographic principle suggesting reality itself is a projection, these concepts force us to rethink everything we know about existence. So which theory left your brain in knots? Was it the idea that every black hole could contain a universe with its own flow of time? Or the spine-tingling possibility that consciousness itself might shape how time bends near the event horizon? Drop your favorite in the comments. We're obsessed with these cosmic riddles, and we want to hear which ones keep you up at night. If you're hungry for more deep dives into the universe's greatest mysteries, hit that subscribe button and ring the bell. The cosmos is stranger than we've been taught, and we're just getting started unraveling its secrets. Until next time, keep looking up and keep questioning reality. The next breakthrough might be just beyond the